Well, good evening, everyone, and welcome to our virtual colloquium tonight. This is the 23rd of October, 2012, and we have a fantastic speaker tonight. Our speaker tonight is Dr. Kendra Sibbernsen. Dr. Sibbernsen is a professor at Metropolitan Community College, which is in Omaha, Nebraska. She recently finished her PhD in astronomy education at Capella University, and she'll be telling us about her dissertation work tonight, which is something I'm very, very interested in. She was looking at, as she'll tell you, she was looking at the Introductory Astronomy Laboratory course for non-science majors, which many of you know I'm very interested in those sorts of topics, and she took a very interesting turn to it, trying to understand how the lab can be used to help students' understanding of scientific inquiry. So, Kendra, we are excited that you're here, and take it away.
Okay, well, thanks for inviting me. I thought I'd go ahead and start by giving you a little bit of background about me and my path to get to this point. I was about 8 years old, and I went to the school library and I checked out a book on stars. And I learned about white dwarfs and red giants and the HR diagram, and I thought that this was incredible, it was fabulous. And so I've always kind of had a spark for astronomy. Well, when I went to my undergraduate institution, I went in and I said, I want to study astronomy. And they said, well, you should probably take physics then. You should probably major in physics and then get into astronomy in graduate school. So that's what I did. I took my physics classes, graduated with a major in physics, and then I went to my graduate school. I went to the University of Nebraska at Lincoln, and I took all of my core physics and astronomy classes there and got my master's degree. And then I was a little burned out, and Michael got a job as the planetarium director at the Grout Museum in Waterloo, Iowa. And so ended up moving there. And about a week later, a week after I moved, I kind of fell into this position teaching physical science at Hawkeye Community College in Waterloo, Iowa. And I ended up teaching like 3 classes that semester, and Hawkeye had just turned from a technical school to a community college, and they didn't have any physics or astronomy classes on the books. So I developed the curriculum for the algebra-based physics sequence, the calculus-based physics sequence, and the astronomy, the introductory astronomy class. And I found that I loved teaching. I really enjoyed it. And I was at Hawkeye for about 9 years, and then a similar position opened up here at Metro in Omaha. And we have family who live here, and we wanted to be closer to them, so I applied and got the position, and we moved to Omaha. Shortly after that time, I started thinking that I wanted to go for a PhD. You know, 1, just for the challenge of it, 2, the pay increase, 3, to become a part of the science education community, you know, astronomy education, physics education, research, and to help students learn how to do science. So I didn't want to give up my full-time job. I love teaching, and I wanted to do the doctoral work in my spare time. And I was looking around, and Capella University kind of fit that bill. I could do all of my education classes online. I had to do 3 one-week residencies, and with Capella's colloquia, their residencies, they do them all over the country. And so it's 1 week long. You can go in, and they schedule them in the summer. They schedule them in between Christmas and New Year's, so it's great for a teacher. And you know, after I finished my comps, I found a wonderful mentor. She was she is an educational psychologist, and I found another committee member who had an emphasis in instructional design for online learning, and Tim very graciously offered to be my other committee member. So he was the visiting professor and the expert in science education content. So when I started thinking about what I wanted to do for a dissertation, I was looking at my practice, my teaching, and the thing that I was least satisfied with were the labs. The astronomy labs were very cookbooky. They were, you know, here's the thing, you do this, you fill out this graph, and then you answer something. And so it really wasn't indicative of what science is. and I didn't feel the students were getting what they could out of the labs. So Tim said, well, here's something that we're working on. Could you take a look at these labs? And these labs were using what they were calling a backward fading scaffold format. And so I looked at it, and what it was a way to emphasize inquiry, getting students to ask scientific questions about some things in astronomy. So my long-term goal for this was to do something with the online. You know, I know that astronomy is a very visual science, and there's a lot of incredible data available. NASA has a lot of data right there on the web that you can use for asking questions, visual pictures as well as numerical data. So I thought, all right, let's go ahead and give this a try, but if we're going to put it online, I want to do it in a responsible way. So my dissertation topic was looking at how well students perform these labs and how well they were able to ask scientific questions, but started off by looking at them in traditional groups versus those doing them individually. Okay. So the purpose of the study is to determine how students in an undergraduate astronomy laboratory, so regular Astro 101 lab, increase their understanding of inquiry working in relative isolation compared to working in small collaborative learning groups. Because I figured if the students who ask the questions on their own do as well as those in the collaborative learning groups, then we could put them online and do that in kind of a responsible way. So the rationale for the study was to allow students to develop and practice inquiry skills using these backward faded scaffolding labs, or VFS for short, and study if students who complete the labs individually are more or less or equally successful at understanding inquiry as compared to those who complete them in groups. So this is all a possible precursor to offering these labs in an online format. My method was a mixed method, quasi-experimental. What we ended up doing was, it was a large university with several astronomy sections. Most of them did the labs in the traditional way, small lab groups, about 3 people in a lab group usually. And one lab group was going to complete the labs individually. Most of them are using computer websites, and so everybody had a computer in the individuals group. So we had these 2 groups, did a pretest, post-test with labs, and then also used an instrument that was qualitative in nature and asked them some questions about scientific inquiry. So the first treatment was individual groups, and the second treatment was individual completion. The data collection, both quantitative and qualitative. The quantitative was looking at the laboratory exercises, one at the beginning of the class and one at the end of the class. And these were graded using a rubric specially based on inquiry. Now, if you look at most of the objectives for a lot of the college classes, all the sciences, chemistry, biology, physics, astronomy, one of the main objectives is to get students to understand inquiry and do scientific inquiry. But you know, I kind of felt that the labs were kind of falling down on that point. So we also wanted to take a look using the qualitative, using an instrument called the VOSI, the Views of Scientific Inquiry. And the one that I used was the VOSI 4. So this instrument was developed by Dr. Renee Schwartz. And the 4 here is one that she developed for pre-service teachers, undergraduate, and I thought that it worked really well with the undergraduate population the general studies Astro 101 group that I wanted to study. And also talked to some of the instructors just to get their observations of the groups versus the individuals to see if there was any differences. Okay, so how many of you are familiar with the DFS Labs? I want to know how much I need to go into this. So you can either like raise your hand or say yay or nay in the chat. Somewhat familiar, should explain, no. Okay, so for those of you that know about it, it'll be a bit of review. Those of you who don't, the backward stated scaffolding approach is, as I said before, focused on inquiry. So this chart is from the Slater, and Shaner article from 2008. And this is where you start up, because if you just give the students some data and you say, here, ask a scientific question, you know, they look at you with deer in the headlights look, and they're terrified and they have no idea what to do. So kind of the idea is that you need to support them enough to get them to a point where they're comfortable with the website or whatever data they're using, and then they can start to ask some good questions. So this process, you have this sequence, and you start off with, okay, here's a scientific research question, and here's how they found their data, and here's the data, and here's the conclusion, so that they can see that whole process from start to end. And then you say, okay, here's another research question. So you're giving them an opportunity to see what good scientific research questions look like. And then, okay, here's the procedure that they used, here's the data. What would you conclude? So then the student has to come up with the conclusion. So you're slowly taking away that support as they get more and more comfortable with whatever you're studying. Okay, then in phase 3 here, here's another scientific research question. Here's their procedure. Okay, you take the data and come up with a conclusion. And then slowly taking away that support. Here's another research question. How would you take the data? What procedure would you use, and so on. And then the last phase here is all you come up with a scientific research question, you figure out the procedure, you find the data, and come to a conclusion. So this is arguably the hardest thing in scientific inquiry, to come up with a good scientific question. And that's what I like about these labs, is that they allow students to do that. All right, and in the process, what you've given them is you've given them like 3 or 4 good scientific research questions that they can maybe modify, maybe change a little bit, and then still have something good and interesting to study. All right, so many of these are kind of a modified DFS style, and that's, you know, just for time purposes, because you want to be able to get these done within a couple hours of the lab. And so most of these have the 5 phases and a final reflection, a conclusion. So phase 1 is generally introduction and exploration. Here's a website that has some data in it. Maybe it's a simulator, but it's got good data, real data, and here you're playing around with it. In phase 1, it says click here. You're doing a lot of hand holding. You know, click this, change this, do these things. In phase 2, it's giving them a scientific research question, and it's showing you data, and it tells the conclusion, or based on what you did in phase 1, and then it says, would you agree or not? You know, so would you agree with their conclusion? Phase 3, here's the question and the data. You know, here's the data. What would you conclude from it? So, you know, slowly taking away that support. Phase 4, here's the research question. How would you collect the data? Okay, now you don't actually have to go through and do the data and come up to a conclusion, but how would you go about it? What is that procedure? And then, and this is what I was most interested in, is the phase 5, the independent research question. You come up with a question, maybe similar, maybe a little bit different, maybe completely off the wall different, but having to do with this particular thing that we're studying. Find the procedure, take the data, and come to a conclusion. So the labs that we were using, there's a number of them. There's some incredible resources on the internet available for students. One of them is a pretty simple sky map. Heavens Above, you may have seen it used for finding satellites in the sky, finding when the International Space Station goes over, but it has a sky map on it for constellations. Now there's others that you could use. There's Stellarium, there's a bunch of other planetarium type programs, But this one's kind of simple, and it's nice because you can slowly change the increments of time. You know, you can move it forward by an hour, or you can move it forward by a day, or you can move it forward by a year, and see how it changes. There's the JPL Solar System Simulator, which is used for the Jupiter's Moons Lab. There's some other of these that could be used as well. I think there's one called Eyes on the Sky. It was in beta last I saw, but you know, kind of some nifty stuff out there that can be used. There's a solar lab, one using the Hubble Deep Field, one using extrasolar planets and a plotter for that, and Galaxy Zoo. So you may have heard of Galaxy Zoo before. This is a citizen science project, and the Galaxy Zoo that we use for this is using the original Galaxy Zoos. So it's no longer taking data, and they've changed it. You know, as their research project has changed, they've changed the interface. But they do have Galaxy Zoo Classic, the Galaxy Zoo 1 available, and I think it's perfect for my introductory astronomy students because it makes them go through, originally go through and learn the difference between ellipticals and spirals and whether the spiral arms are going clockwise or counterclockwise, and irregulars, and how to tell the difference between a star. And so they have to go through that before they start classifying galaxies. All right, so the ones that we used were the heavens above, and this is kind of what it looks like, very simplistic, but you can see the constellation. So the students might choose, excuse me, a particular constellation, and you can move it forward by minutes, hours, days, months, years. And then the other lab was the Galaxy Zoo one. So the heavens above, the constellations, was looking at how constellations move in the night sky, the cycles in the night sky, and then Galaxy Zoo has to do with classification of galaxies. And this is what Galaxy Zoo Classic looks like, the Zooniverse project. They have the Moon Zoo. Ken mentions planet hunters, and they were looking for Kuiper belt objects, and just a whole bunch of really neat stuff. But I love the simplicity of the original Galaxy Zoo. All right, so these were deemed to be functionally equivalent. You know, the math that you need to do this is, you know, pretty low level, about the same. And so looked at, for the quantitative measurement, one of the first experiment, one of the first exercises they do, and one of the last ones. So kind of like a pretest, post-test thing. So these were graded with an evaluation rubric based on inquiry, and did a paired sample t-test, and also used the VOSI and instructor interview. And the VOSI was coded with descriptors, looked for specific words, and written narrative in the interviews, and then compared the qualitative and quantitative results. So the rubric was asking some basic questions. Is the research question, so this is all phase 5 stuff. We just looked at that independent research question that they developed and saw, you know, how good was the question stated? Did it show creativity? Was the plan appropriate for answering their question? Did the presentation explain everything? Is the data presented clearly? Was there adequate data? Sometimes this is a little hard to do because it's a pretty short time frame, you know, but you want to make sure that they get enough data points. Are they able to communicate it? Is the conclusion clear and unambiguous? Is the conclusion based on and supported by the data and overall presentation? So just kind of a little simple rubric there to see if it changed any. So the summary of the findings. All exercises were evaluated using the rubric by an astronomy instructor, so somebody who taught astronomy before but who had not taught the DFS labs and was not told which lab was done first. There were increases in both conditions of scores from the first to the last lab, both the individuals and the groups. Both data sets were tested for normality and equality of variances, and they were all found to be normal. And so they weren't skewed in any one direction. And something kind of interesting, the individuals had a slightly higher mean for the first lab. And it's thought that this was because by talking to the instructor through the interview, they spent more time on it initially in the beginning. So they wrote more, they tended to write more, and they took more time on it, perhaps because, you know, it was all on them. In the groups, they could split it up and do the cognitive work as well as the actual clicking and doing the work. So here's what the values were, and this was the individuals the first week, this is the individuals the last week, and this was the average of their scores on that rubric. Here's the groups the first week, and here's the groups the last week. These were all face-to-face groups. So this was before we put them online. So more deviation that first week, less deviation this last week. So even though the individuals went up, it wasn't quite as much because they kind of had a higher score to begin with. So we had quite a few groups. Each of the groups had about 3 students in it, and we ended up with 25 groups, and the increase for the groups was significant. The two-tailed p-value was less than 1/10,000. So, you know, real strong evidence there. The individuals, however, because it had to be paired, you know, you had to have both the first lab and the last lab, it was originally a class of 18. And for some reason, you know, students didn't have one or the other, so I couldn't pair them up. And that means that the sample size dropped down considerably. So it ended up to have 12, and that had the p-value turn out to be not significant. So let me step back a minute here. I did a t-test on these, and these 2 sets of data were not found to be significantly different from each other. And these 2 sets of data were not, oh, we can't see, sorry. Do I have a pointer here?
Yep, that's working. It's working good.
Okay. I'm just dropping. Okay. Well, I'm looking at these first 2 columns, or the first 2, columns here. So these were not found to be significantly different the first week, the individuals and the groups, and the individuals and groups for the last week were not found to be significantly different from each other. All right, but looking at the values in the sample size of the individuals, like at least 2/3 of them were increased by a couple of points. There were like 2 in here that were less by 5, you know, so you had a couple guys in there who had like a really bad day. And so this ended up to be not significant. Both conditions increase their understanding of inquiry from the beginning to the end of the course. 15 individuals. Okay, so this is the qualitative summary of the finding. This is what happened with the VOSI. Found that both the individuals and groups seem to increase their understanding of inquiry from the beginning to the end of the course. So 15 individuals and 113 students in groups. Some of the questions from the VOSI, this is a 7-question open-ended questionnaire asking about some things with inquiry. And some of them changed, but most had an increase in understanding of inquiry. The most dramatic of these was when asked, how do scientists do their work? So originally, there was about 20% of groups and about 13% of individuals give kind of a naive response to this. You know, they might say they wear lab coats, they use a telescope, you know, and afterwards, there was hardly anybody who gave a naive response when asked how scientists do their work. So to give you kind of an example of the data that I got from this, just put them into columns. Classifications, how do scientists do their work? So that naive response here, maybe some things about how scientists do their work. They experiment, they run tests, you know, they do research, they do studies, but kind of generally. And then a typical response would be, you know, scientists have hypothesis, and then they do a test, and then they go back and change it, and just kind of the basic response for the scientific method. And then in an informed view, this is maybe somebody who would say that, you know, all that other stuff, they do research, they do tests, they take data, they show evidence, but then also they communicate with other scientists, they perform, they write peer-reviewed journal articles and like this. So what I was mainly interested in is this. The pretest, you know, general response, typical response, that's where most people were. But then afterwards, they tended to have more of a complete answer, you know, more typical responses, and then fewer of the naive responses. One of the big changes that I thought was kind of interesting, especially in this first question, was the terms or phrases used. So you can see here that experiment was used, the word experiment was used quite a bit, pretest and post-test. But look at here, the second one, pretty big change. So scientists ask questions. So this seems to be related from the labs that they did, you know, because we're hammering them on ask a research question, ask a question, ask a question. So 15 people beforehand said ask questions. Afterwards, there was like 42 people that used those terms. And, you know, kind of similar things here all the way down. Fewer people use the term scientific method, and fewer people use the term test theories. They didn't do that in the lab. You know, they didn't use the terms in the laboratory write-ups. So it did ask a question and make conclusions. So more people use the terms, make conclusions in the open-ended VOSI instrument, the post-test. So here's kind of a summary of what I found from all of the questions. And the groups and the individuals seem to fall right in line with each other in terms of how well their views on inquiry changed. So some of them had no change or small changes. Like, for example, question 4 here, you know, the question was something about if a researcher were to look at the teeth of this animal, and they, like not an anthropologist, but a paleontologist looked at these different animals and saw that the meat eaters had sharp teeth, and the animals that ate the grasses and whatever had lumpy molars. And is this a scientific process or not? And then question 4 said, do scientists have to follow the scientific method? So it's kind of their definition of the scientific method, like what you learn in middle school versus are there many pathways to understanding science? But in most cases, you know, slight increases for all of them, a couple pretty big increases with question 1 and the question on how scientists justify their claims. And then this kind of strange little thing in question 3 where there's a slight decrease in the groups and a slight increase in the individuals. So this might be, you know, like just noise in the data, or maybe this lab group, you know, had a different conversation than everybody else did. But for the most part, they seem to be right in line with each other, the groups and the individuals. So in general, the groups and the individuals completing the DFS labs have similar changes on the views of scientific inquiry instrument. More students use the word ask questions and make conclusions in the post-test VOSI rather than scientific method or test theories as they did in the pre-test administration. And I think this is because they felt that they were doing science. They put themselves in the roles as scientific researchers, and that's what they did in the lab, is they asked questions, they found the data, and they made conclusions. The interview with the instructor of both conditions, so the instructor taught both the groups and the individuals. suggested an increase, and the person who graded the exercises, both suggested that their students had an increase in understanding and sophistication in their writing, like how they used the words related to science and how they were able to ask those scientific questions in their explanation of inquiry. So when I finished this, the recommendations that I came up with is, I felt pretty confident that, the groups and individuals do pretty well at learning how to do inquiry. And so I felt confident that I could put these in an online format and see how my students did. So went ahead and did that, offered the Astronomy DFS Labs online, and I wanted to provide opportunities for peer-to-peer interaction. Rather than having them work in groups to do the labs, I wanted them to come up with their own research questions, but allowed them to participate in virtual science conferences. So if you go to a scientific research conference or an education conference or any of these conferences, you have people putting up posters and talking and communicating. So this is what I have my online students do, is I have them take their data, their phase 5 research, their question, their procedure, their data, and their conclusion, and they post it into the message board, into the forum. And then I give all the students that rubric, that inquiry rubric, and then I have them grade each other. Well, not grade, but evaluate each other. And so in that process of evaluation, they are learning that while they're seeing other people asking scientific research questions, and they're able to get a better feeling for what it is to have a good research question, or how much data do you need to have strong evidence supporting your conclusion. And in addition to the astronomy, and the astronomy is great because there's so much available online, I wanted to add a couple geology labs, meteorology, and physics so that I could offer physical science survey online, so an introduction to physical science in an online format. And I've done both of those things since that time. So I've been doing the online DFS Astronomy Labs for the last 2 years and have had really good success with them. I've been really pleased. And I started last year with the physical science labs, so using some of the astronomy and then some other ones as well. And that class has been wildly popular. It's been really successful. The students really enjoy that. So I thought I'd share with you some of the end-of-class reflections in the Astronomy Laboratory. These are my students, and these are ones who have taken the DFS lab online. And so here you have a student saying, I enjoyed the labs because they were challenging because it demanded you to think logically about a scientific question. I found it to be exciting and at the same time frustrating. Isn't that how science goes? The labs weren't anything you could rush through. They required plenty of focus, but I learned a great deal working through them. So this is a common theme. They say that they generally liked them, but they were not easy. They were hard for these students. And I think that's all right. That's what science is about. So here's a student that says, this is the first online class I've ever taken. And I believe this was a student who was a K through 12 teacher, and she was going back for a science certification. This is my first online class that I've ever taken. Laboratory experiences for me have always been in a lab room with a teacher and other students present. This part of the lab was more difficult for me because I've always worked in a group, worked with others in a lab setting. Most of the computer-generated labs were good, but it took me about 3 weeks before I got the hang of them. And this seems to be a common thing for my students as well. Once they get through maybe the first couple weeks, I kind of have to hold some of their hands for a while because asking that first scientific research question is really traumatic for some of them. They'll ask me, they'll say, well, what do you want me to ask? And I'll say, well, ask what you want. That's the point. You got to come up with your own question. And it's really hard for them to come up with something and then come up with data and not know if it's the right answer or not. How do I know if I have the right answer? Well, you're taking the data. You're the scientist. You're the expert in this now. And then here's another quote. I was a bit concerned how I would learn in an online laboratory. but I thought it worked out well. I hadn't previously no idea, though, why would I, that there were so many online avenues to study astronomy. I enjoyed the personal responsibility for the outcome of my lab, and that meant the grade was a direct reflection of my work. So, since I've had such success with the online astronomy DFS Labs and the physical science DFS Labs, my big project for this year is to develop a set of algebra-based physics labs first semester focusing on inquiry. And I'm the lead online faculty member for science at Metro, and I'm also a part of an iPad group. We've got a bunch of iPads at the college, and we're testing them out in different ways. And I've found some apps that I think are really amazing. There's video physics for iPads and iPhones and timers, and they automatically have an accelerometer in them, a 3-dimensional accelerometer, and microphone, sound analyzer. And I think that I can come up with enough labs to put together an online, where students use their smartphones to take data, and then they'll send me their videos and their graphs about their data, their scientific data that they're taking with their own technology. And we'll see how that goes. But I think that's about it. Here are my references, and I will thank you for your attention, and I will take questions.
Kendra, do you have an example of like the lab data sheet or something like that you would use for one of your online labs, inquiry labs?
What do you mean? Have you seen the DFS Labs?
Not yet, no, but I think I'm going to be doing some looking later on tonight.
Okay. Yeah, take a look because I'm using the same ones that Tim linked. He has, I've developed a couple additional ones myself, and I've made a few small changes, but it's mostly the same labs that he has in the book, the Engaging in Astronomy Inquiry. So if you can get a hold of one of those workbooks, it'll give you a great opportunity to see. And I just take those, and the only differences that I'll make is where it says, draw this graph. Well, I can make my online students draw the graph. They can use some kind of drawing tool, or they can draw it on paper and scan it and send it in. But instead of like circle this, I'll say highlight this because it's easier to do in Word. But it's pretty much the same way. As long as the techniques are solid and written well, my online students don't tend to have problems with them. And so you kind of need to keep that in mind if you're developing them. But yeah, it's the same ones that he's using. And then I can share some of mine. If you get my email off of the last slide here, you can email me and I can send you some of the ones that I have.
I've got a similar question to what Cheyenne asked in the chat. If you could go back to slide 20, which was about the terms the students use before and after to describe science. Yeah, that one. Oh, wait. That's it. That one, yeah. So I'm seeing that there's an increase in the use of the phrase ask questions and the phrase make conclusions, but a decrease in the phrase scientific method and test theories. So what I'm wondering is, do the students think that these are distinct, separate ideas, or are they just putting the same ideas of scientific method and test theories into words they understand, such as ask questions and make conclusions?
I think that it's kind of both of them. The collect and analyze data only went down by 3 people. So, maybe they wrote it in the first part and then didn't in the last part for whatever reason. They weren't thinking that day. But, I would think that in the beginning they would use language that they would more be used to. So what's kind of happening here is in the beginning they're kind of relying on what they've learned before, make a hypothesis and, what scientists are supposed to do, use the scientific method. But through the process of the labs, you're really hammering them on ask a scientific research question, and, you go through the process, the procedure, and you analyze the data, but kind of the emphasis is on the asking of the question one, and what do you conclude? Because then you hit them with that summary at the end. You're doing a reflection at the end, and you're saying, okay, well, what did you find out about all of this? What's your overarching summary of the whole thing? Okay, so Tim asked, what's the hardest part of scoring the VOSI? Oh, it's probably putting them into categories. It wasn't so difficult, but sometimes, if the students were particularly ambiguous trying to figure out what section that they go into, whether you consider this naive, because occasionally they'll just throw something that's completely off the wall. But for the most part, it wasn't too difficult to figure out. Renee has a guide, kind of like a scoring guide, and gives you some ideas of what some typical responses are for the VOSI. And so, it's just a matter of going through it. If you have over 100 of these things, it's the sheer paper and going through them all step by step.
Well, Kendra, I want to thank you again for an absolutely outstanding presentation. I know that we all enjoyed it very much, and the work that you're doing here really shows a lot shows us a lot about how do we really engage students in the ideas of scientific inquiry, and you're beginning to extend this into some other domains and being able to use different technology. And I think this is really, really exciting stuff, and we really appreciate you talking to us.
Okay, well, thank you for having me.